Good morning, one and all.
Good morning, sir.
Yeah, today the topic is shift registers. So, in the last class, we have come across the definition and design of register. What a register is? A register is nothing but group of flip flops. Means if we can put multiple flip flops on one place, then we say it's a register. Let us say I will call this register as A, consisting of 1, 2, 3, and 4 flip flops. Let us call the flip flops as A3, A2, A1, and A0. So since this register contains 4 flip flops, and we know each flip flop can contain 1 bit, so all 4 flip flops together can hold 4 bits of information or 4 bits of data. So we call this register as a 4-bit register named A. So a register is group of flip flops. See, 1, 2, 3, 4. There are 4 flip flops, and each flip flop can store only 1 bit. So all 4 flip flops together can contain 4 bits data. So we call this register as a 4-bit register. In the last class already we have seen how 4-bit registers are constructed and used. Today the topic is shift registers. Shift registers are of 2 categories. One is called left shift register. The second one is called right shift register. Means shift register shift the contents of the register. Hence we call it as a shift register. The content of a register can be shifted. The contents of a register can be shifted both left as well as right. That's why we call it as a shift register. Now let us see how do we construct a shift register. For example, to understand in a better way, I'm taking an example of 4-bit right register here. 4-bit right shift register. How it is constructed, we will see. Okay. So I'm taking the help of 4 flip flops since the size of the register is 4 bits. So 1, 2, 3, 4. And I have been taking all of them as type D only. All flip flops are of type D. Since they are flip flops, they will be having common clock. The common clock is common for all registers. The clock is common for all the registers. Let us call this register as A, this register as A3, this register as A2, this register as A1, this register as A0. So the first register, the first flip flop of this register receives input called as SI, where SI stands for serial input. SI stands for serial input. And the output of the first register, that is A3, is connected to the input of the second register. The output of the second register is connected to the input of the third register. The output of the third register is connected to the input of the last register. The last register output is called SO, that is called serial output. SI is called as serial input. SO is called as serial output. So this is how shift registers are designed. So to understand in a better way, I will take a simplest diagram. Let us say my register looks like this with the 4 flip flops. The flip flops are called A3, A2, A1, and A0. The first flip flop receives input from serial input. The output is called serial output. This is called as right shift register. This is called as right shift register because this register can shift its contents towards right. For example, after shift, what will happen? We will see. Means if this is the register given, if you shift the contents, means if you assign this clock, if this clock is fired, what happens? A3, A2, A1, A0 becomes, see earlier they were A3, A2, A1, A0 with serial input and serial output. After shift, it will comes like this. The serial input enters here. This A3 comes here. This A2 comes here. This A1 comes here and A0 goes out. This is serial output and this is serial input. So this A0 comes out, A3 occupied here, A2 comes here, A1 comes here, A0 goes out. So if you see A3, A2, A1, A0 become SI, A3, A2, A1. What goes out? A0. So we are shifting the contents towards right. That's why we call it as right shift register. In the similar way, we can also construct left shift register too. Left shift register. Similar way, I have 1, 2, 3, 4 flip-flops. So I'm writing inputs this side because it's a left shift register. I'm just changing something. So this is my serial input. This output, this is called as A0. This is called as A1. This is called as A2. This is called as A3. This is the serial output. See, I am just taking the reverse order of the flip-flops. So this is a common clock. If this is the clock and these are the 4 flip-flops, of every flip-flop is of type D, named A0, A1, A2, A3. If you can apply this clock, these contents will be shifted towards left. To see, we will see like this. For example, if the flip-flops are A3, A2, A1, A0, and if this is your serial input, this is your serial output. After shift, what happens? We will see. After shift, what will happen? This SI enters inside, A0 comes here, A1 comes here, and A2 comes here. This is serial input, this is serial output. What goes out? A3 goes out. Means the contents of this register are shifted towards left. That's why we call it as a left shift register. That's why we call it as left shift register. Got it? Is it okay?
Yes, sir.
So this is all about left shift register and shift registers. Now we will see another operation on these registers and shift registers that is called as serial transfer. The topic is serial transfer. What do you mean by serial transfer? Serial transfer is nothing but transfer the data between registers 1 bit by 1 bit. Means we will transfer the contents from one register to another register in a bit by bit mode. Got my point? For example, to understand the serial transfer in a better way, I have been taking the example of 2 registers. Let me consider 2 registers A and B. Both are of 4 bits. Let us take an example. See, this is how the design looks like. So I have 2 registers A and B. Fortunately, both are of 4 bits. Okay. Let us say this is my register A and this is my register B. Both are having a capability of shifting its contents. So this is also shift register. This is also shift register. Okay. So let us write the names A3, A2, A1, A0. These are called B3, B2, B1, B0. Since this is a shift register, it contains its serial input and also serial output. Okay. The serial output of the first register is connected to the serial input of the second register, SI. And this register is also having, of course, its serial output is 4. So we will take a feedback loop and connect it back. So this is the connections. Means the first register A output is connected to the second register's input and also connected back to the first register's output. Now we will see what happens, the contents of register A and register B after time pulse. Let us say. Before we start, register A shall have A3, A2, A1, A0. Register B shall have B3, B2, B1, B0. Means clock is not given. At first clock means when you press the clock, what happens? You know, A3 comes here, A2 comes here, A1 comes here, A0 goes out. So A0 is occupied by A1, A1 is occupied by A2, A2 is occupied by A3, A3 is occupied by SI, where SI is ila connect chesam kada. So what goes out? A0. A0 come and join here. So this is A0. So this happens with the register A. See now this A0 comes out and connected to B3. So B3 occupied by A0, B3 comes here, B3 comes here, B1 comes here, B0 goes out. This B0 will go out. See, this is how it got shifted. Now you see another clock pulse. Again, now what happens? A0 comes here, A3 comes here, A2 comes here, A0 come and join at the back because A1 comes out. And also A1, A0, B3, B2, B1, B0 left out. Now we apply clock again. If you apply clock again on this register, A1 comes here, A0 comes here, A3 comes here, A2 comes here, A1 comes here. This is A0, this is B3, B2 goes out, B1 already, B1, B0 all out. Now let us do clock pulse for what happens. So here A2 also comes and join here. Now if you shift here, this A2 comes here, this is A1, this is A0, A3, A2, A1, A0, B3 goes out, B2 goes out, B1, B0. This A3 come and join at the back. See, after 4 clock pulses, both registers become A3, A2, A1, A0, A3, A2, A1, A0. What did we do? We have copied the contents of this register A into this register B. This is how it happened. Is it clear?
Sir,
Yes.
sir, it's not clear, sir. Can you show the screen little bit up, sir? It's not visible clearly.
Okay.
Okay, sir.
So that's why this topic is called serial transfer. Transferring the contents from register A into register B, one after the other. See, if you don't use this feedback loop, what happens? A not moved, A1 moves, A2 moves, A3 moves, but we will lose the contents. It's not like cut paste. It's like now copy paste. See, after 4 clock pulses, both register A and register B became same. The contents of register B will be lost. So this is called serial transfer. This is called serial transfer. The next and most important topic is universal shift register. Is the page visible?
Yes, sir.
Okay. Now we will see what do you mean by universal shift register. This is one register which is called as universal shift register. Why we call it as universal shift register? Because a universal shift register performs various operations. One is it performs right shift, it performs left shift. See, same register performing different operations. Right shift, left shift, intact means leave the register as it is, and also it performs parallel load means load the contents into the register at the same time. So universal shift register is capable of doing left shift operation, right shift operation, parallel load operation means a new content will be loaded into the register, that we call it as a parallel load operation. And also it may leave the register intact, means leave the register as it is. If you see here, 1, 2, 3, 4 flip-flops were there. How many flip-flops are there? 1, 2, 3, 4 flip-flops are there. Means this is my register. A register is a group of flip-flops. So this is my register. What is the name of the flip-flop? A0. Second flip-flop is A1. Next flip-flop is A2. Last flip-flop is A3. Understand? So all flip-flops are of type D only. It's a D type, it's a D type, it's a D type, it's a D type. So I'm using 4 flip-flops of type D named A0, A1, A2, A3. So this is a D type flip-flop, you know very well. D is very simplest flip-flop. So the inputs of every flip-flops are coming from a multiplexer. Every flip-flop input is connected to multiplexer. Every multiplexer is of size 4/1. Means there will be 4 inputs, 1 output. So multiplexer 1 output is connected to the flip-flops. That's what we have to understand. Now you see, what are the 4 inputs of this register? this multiplexer. See, the zeroth input is coming from A3. This zeroth input is coming from A2. This zeroth input is coming from A1. This zeroth input is coming from A0. If you look at first input, comes from serial input. This first input is coming from A3. This first input is coming from A2. This first input is coming from A1. If you look into second inputs are coming from A2. Second input is coming from A1. This second input is coming from A0. Now you see the third input. Third input is connected to I3, I2, I1, I0. So there are two selection lines S1 and S0. There are two selection lines S1 and S0. For example, if you make S1 and S0 as 0, 0, now the question is what will be the value of A3, A2, A1? A3, A2, A1, A0, what will happen? See, if the S1 and S0 are 0, 0, in every multiplexer, the 0th input will be selected. So what is this 0th input for A3? Nothing but A3. This 0 input is coming from A2. This 0 input is coming from A1. This 0 input is coming from A0. See, A3, A2, A1, A0 it will be A3, A2, A1, A0 only. Means this is called intact. Leave the register as it is. Now you see, if you give S1, S0 as 0, 1, first input will be selected. Input 1 will be selected.
Sir,
Sir.
the screen is showing blur, sir.
Oh, is it so? Just give me a minute.
Yes, sir.
Amma, can you see my PPT?
Yes, sir. Now I can see, sir.
Okay, now let us try to complete this topic with the help of PPT. Don't worry. So this is the design of a 4-bit universal shift register. So what is the specialty in this universal shift register is? See, there are 4 flip-flops A3, A2, A1 and AN. See, there are A3, A2, A1, A0 as flip-flops. And all flip-flops of type D only. This is a D type, this is a D type, this is a D type, and this is a D type. The D inputs are connected to the outputs of the multiplexer. All flip-flops D inputs are connected to the multiplexer. The multiplexer receives 4 inputs: 0th input, first input, second input, and third input. First input, second input, third input, 0, 1, 2, 3 inputs are connected to different lines. Now we will see what will happen if this S1, S0 as 0, 0. We know if S1 and S0 as 0, 0, we have to see what will happen. The logic is very simple. If S1 and S0 is 0, 0, from this multiplexer, 0th input will be selected. From this multiplexer also 0th will be selected. From this multiplexer, 0 will be selected. From this multiplexer, 0 will be selected. So if all 0th inputs are selected, now let us see what is this 0th input. This 0th input is coming all the way from A3. So we will get A3. We'll get this 0 input is coming all the way from, you see, all the way from A2. So we call it as A2. This 0 input we are cutting from A1. This 0 input we are cutting from A0. Okay. So if the multiplexers are getting inputs from 0th inputs, then the register becomes, the register earlier was, what is the content of the register before going to do any operation? A3, A2, A1, A0. But even after S1 and S0 made 0, 0, still the register is A3, A2, A1, A0 only. So we call this as no change operation because the content of register are intact. Now let us try what will happen if the contents of S1 and S0 becomes 0, 1. For example, if S1 and S0 are 0, 1, here the first input will be selected. Here also first input will be selected. Here also first input will be selected. Here also first input will be. Now you see, this first input is coming all the way from SI, serial input. This first input is coming from A3. This first input is coming from, you see, from A2. This first input is coming from A1. A1. Understand? See, the content of the register is A3, A2, A1, A0 before. But now, if you make S1 and S0 as 0, 1, the content of register becomes S1, A3, A2, A1. The content of the register becomes S1, A3, A2, A1. Can you tell me what happens? A3, A2, A1, A0. A0 is lost. A0 occupied by A1, A1 occupied by A2, A2 occupied by A3. The gap A3 is filled by serial input. What is this operation called?
Right shift.
Got my point? In the similar way, let us try to go ahead with the next one. For example, if you take S1 and S0 as 1, 0. So here second input will be selected, second input will be selected, second input will be selected. Here also second input will be. If all second inputs are considered, the second input is coming all the way from A2. So if S1 and S0 is 0, 0, 1, 0, first one will be A2. The second input is coming from A1. The second input is coming from, this is A1. The second input is coming from A0, A2, A1, A0. The last second input is coming from serial input. Serial. So the register was earlier A3, A2, A1, A0. Now after making S1 and S0 as 1, 0, it has become A2, A1, A0, S1. See what happened? A3 is lost. A2 occupies A3, A1 occupies A2, A0 occupies A1, A0 occupied by SI. Can you tell me what is this operation called?
Left shift.
Left shift. This means when S1 and S0 is 1, 0, the operation performed is left shift. In a similar way, let us try the last option, that is called when S1 and S0 is 1, 1. If S1, S0, 1, 1, the third inputs get the opportunity to be multiplexed. So third input here, third input here, third input here, third input here. Hello, class lo unnanu call chestane. Hello, class lo unnanu 11:10 call chestane. So when S1 and S0 is 1, 1, third inputs will be selected. See, the third input is coming from I3. I3. Here third input is coming from I2. I2. Here third input is coming from I1. I1. Here third input is coming from I0. I means the register was earlier A0, A1, A2, A3. But when S1 and S0 was made into 1, 1, the content of the register is I3, I2, I1, I0. What we call it as? We call it as parallel load. The registers will be filled with new value coming out from external world. So we call it as parallel load. Parallel load is an operation of pushing new content into the register. The register was earlier A0, A1, A2, A3. But once you make S1 and S0 as 1, 1, the new values I0, I1, I2, I3 were fed into the register. That's why we call it as parallel load. This is how we can understand universal shift register. This is how we can understand universal shift. Is it clear? Is it clear?
Sir, once can you show the theory path, sir? Universal shift.
Which one?
Theory path, sir.
Which path?
Previous one, sir. Theory part, universal shift. Sir, slide number 84, sir. I mean.
Which one?
Yes, sir, exactly.
See, These are all universal shift register facilities. I have explained you. A universal shift register will have a clear control to clear the set to 0. See, this flip flop, this register is having a clear input. If you press this clear input, all flip flops will be set to 0. That is the first point. A clock input to synchronize the operation. Of course, since it is a register group of flip flops, it have a clock. Third point, a shift right control. The register is doing shift right. A shift left control, we know the register is doing shift left. A parallel load control, we know when S1 and S0 has 1, it conducts parallel load. And N parallel output lines. Yes, we know A3, A2, A1, A0 are the output lines. And a control state that leaves the information in the register intact. Means the register can be left as it is by making S1 and S0 as 0, 0. That's what he explained. Understand?
Yes, sir.
These are the features of a universal shift register. Performs 4 operations: left shift, right shift, intact, parallel load. And they have a clear input to clear the register, clock input to synchronize the operation, and parallel load inputs. I through I2, I1, I0 are the parallel inputs. This is the function table of universal shift register. This is how universal shift functions. So by this, the topic registers is over. Now the topic is counters. What is a counter? I'll tell you, counter is nothing but a register. First thing you have to remember, a counter is nothing but a register. But the fun here is, if the content of a register moves in a specific way, we call it as a counter. For example, if you take a register with 4 zeros, for example, let me draw. For example, I have a register with value 0, 0, 0, 0. I have a register with 4 zeros. Okay. So this is a register only because it contains 4 flip-flops. But if I give clock, what happened? It moves to 0, 0, 0, 1. Let us say. See the fun here. So a register of 4 bits, if it goes from 0 to 1, after 1, if it goes to 2, after go, it goes to 3, that is called 0, 0, 1, 1. And 4 and 5 and 6 and 7, 8, 9, 10, 11, 12, 13, 14, 15. That is called last 15 means all ones. And all ones after 4 ones, if it goes to back to 0, 0, 0, 0, let us say, if it go back to 0, 0, 0, then we say it's a counter. So a counter is nothing but a register which moves in a specific sequence. So a register is capable of 4 bits, let us say. There are 4 bits in a register. If all 4 flip-flops goes from 0 to 1, 4 zeros to 4 0 1, 0 0 0 1 to 0 0 1 0, then to 1 1, then 1 0 0 1 0 1 1 1 0 1 1 1 1 0 0 1 0 0 1, and so on and so forth. If it goes in a specific sequence, we call it as a counter. That's what counter means. Counter, a register that goes through a prescribed sequence of states. If the content of a register changes in a prescribed sequence, we call it as a counter. So counters can be constructed using 2 types. There are 2 types of counters. See, it's a counter. See, the name itself will tell you counter means which counts. Whenever you apply some clock pulse, a counter keep counting. For example, a binary counter counts 0, 1, 2, 3, and so on and so forth. If you take even counter, it counts even numbers 2, 4, 6, 8, 10 like this. If you take an odd counter, it counts 1, 3, 5, 7, 9, 11, so on and so forth. If you take a BCD counter, it counts 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Because BCD numbers ends at 9, it go back to 0. So counter nature depends on what sequence it is counting. So that is nature. This is how they were designed. What is the design behind REPL counters, synchronous counters? Counters can be designed in 2 ways. One is called REPL counter. The next one is called synchronous counter. What makes both of them different is very simple. In REPL counter, there will be no common clock. Means since it is a counter, it contains flip-flops. If all flip-flops receives the same clock, we call it as a synchronous counter. In synchronous counter, the clock inputs of all flip-flop receives common clock. In REPL counter, that will be not there. The clock inputs of flip-flops are connected to different inputs. We can simply remember like this. If there is a common clock, synchronize. If there is no common clock, ripple. That's all. Is it clear? Is it clear?
Yes, sir.
Now we will see first ripple counters, then we can go to asynchronous counters. The first topic is ripple counter. So ripple, see the counter name, see it is a ripple counter, means there will be no common clock. It's a counter, means having group of flip-flops. It's ripple in nature, means no common clock. It is binary in nature, means it counts binary numbers. Means if you take 4 bits, they goes from 4 zeros to 4 ones and back to 4 zeros. Clear? Is it okay? That's what we have to understand from this title. It's a counter, means it counts. Okay, what it counts? It counts binary numbers. How do we design this in a ripple fashion? Means the contents of this sequence counter designed in ripple fashion, means there will be no common clock. I will show you the diagram of binary ripple counter. You see, this is the diagram of a binary ripple counter. First thing should flash into our mind is it is a ripple counter. Okay, if it is a ripple counter, see these are the clock input of the first flip flop. See, this is my first flip flop. Its clock is connected to some external input called counter. See, this clock is connected to A0. This clock is connected to A1. This clock is connected to A2. Okay, is it clear? Since it is a ripple counter, the clock inputs are not to a common source. You see, this input is connected to counter. This clock input is connected to some other source. This clock input is connected to some other source. This input is connected to some other source. That's why we call it as a ripple counter. In ripple counter, we will not find common clock. I show you common clock. If you see this diagram, see the clock input of this first flip flop, clock input of second flip flop, clock input of third flip flop, clock input of fourth flip flop. All of them are connected to the common clock. Is it clear? If all clocks are connected to common line, we call it as a synchronous counter. If not, we call it as a ripple counter. The first thing you have to clear from this diagram is very simple. This is not having a common clock. This is not having a common clock. This point is clear. Since this diagram is not getting common clocks, so we assume that it is a ripple counter. We assume that this is a ripple counter. Is it clear? Is it clear or not? Let us start counting this clock. For example, I have 0, 0, 0, 0 here. For example, my current values in register is 0, 0, 0, 0. Okay. Now we will see what happens. For example, if this count is active, I have pressed this count. Got my point? If this count pulse is given, what happened? This clock becomes active. Since this clock becomes active, see the T input of, say there I am using 4 T flip-flops in this diagram. I have 4 T flip-flops. All T inputs are connected to logic 1. Let us go back and see how a T flip-flop works, then you'll understand. T flip-flop, what happens? If T is 0, no change. If T is 1, the content will be complemented. So here, in the design of binary ripple counter, I have been using 4 T flip-flops. I have been using 4 T flip-flops. It's a T flip-flop. It is a T flip-flop. It is also a T flip-flop. It is also a T flip-flop. Since I have been using 4 T flip-flops and all T flip-flops are connected to logic 1, means every flip-flop is ready to complement. Yes or no? Because we know in a T flip-flop, If the input T is 1, then it will complement the present state. That we have to understand. If the value of T is 1, then flip-flops are ready to complement. See, it's flip-flop. All 4 flip-flops T inputs are connected to 1. Hence, all flip-flops are ready to be complemented. But for what we are waiting? They have been waiting for the clock to be active. Yes or no? They have been waiting for the clock to be active. So flip-flops are ready to complement because the T input is connected to 1. But when they will complement? If and only if clock is active, because we know flip-flop gets excited only when clock is excited. So now you see I have given my count as 0. Count 0. Says 0. There is a bubble here. Can you see the bubble here? Can you see the bubble? For example, I have given my count as 0. If the count is 0, since this bubble is 0, there is a bubble means complement. So 0 complement is 1. So the clock input of first C flip-flop is highlighted. Means this clock becomes active. If this clock is active, this 0 becomes 1. Because I told you this T is 1 already. Since this clock is active, the first flip-flop that is called A0. So this is 0, 0, 0. So this 0 becomes 1. Got my point? So if this 0 becomes 1, then the value of A0 is 1. If the value of A0 is 1, it comes like this and connected here, you see. If the value of A0 is 1, 1 complement means 0. So this clock will not be active. If this clock is not active, means this flip-flop will not work. If this flip-flop not work, this flip-flop also stops working. This flip-flop also starts working. So the first flip-flop only changes from 0 to 1. The rest of all flip-flops stay at 0. See, we have been counting from 0 to 1. Now again give clock 0. Again you give clock count. What happens? Again 0. It becomes 1. Again this clock becomes active. See, because already there is a 1. So 1 becomes 0. 1 becomes 0. Means A0 is 0 now. If this A0 is 0, it comes and connect here. See, if A0 is 0, then 0 becomes 1. Means this clock is also becomes active. This clock also becomes active. If this clock is active, then since T is 1, this 0 also becomes 1. If this is 1, A0 is 1. So if A0 is 1, 1 complement 0, this clock is inactive. If this clock is inactive, this clock is also inactive. So these zeros will continue. This becomes 0, this becomes 0. Understand? See how we are counting? We have started with 4 zeros. 0, 0, 0, 1. Next 0, 0, 1, 0. Next you give 0 again. I will clear this. Now you see, for example, my currently I'm having 1. I will go to the last pulse. 1, 1, 1, 1. At present, I have 1, 1, 1, 1. For example, if I give count, what will happen? We have to see. If count is active, since this T is 1 already, this T is also 1 already, this T is also 1 already, this T is also 1 already, because every T input is connected to logic. See, if I make this count as active, means if I give 0 to count, because of this bubble, it becomes 1, means clock becomes active. If clock is active, since T is 1, the present state T becomes 1 becomes 0, because T flip-flop complements. If this is 0, the A0 becomes 0. If this A0 is 0, since it is connected to this clock becomes active. If this clock becomes active, this T flop also complements this one. So it becomes 0. If this is 0, means A1 is 0. If A1 is 0, this clock is active. If this clock is active, since T is 1, this flip-flop also complements becomes 0. If this is 0, means A2 is 0. If A2 is 0, this clock becomes active. If clock becomes active, this 1 becomes 0. So we have started with 1, 1, 1, 1 and ends with 0, 0, 0, 0. Because we know binary numbers starts from 0, 0, 0, 0 and continue counting till 1, 1, 1, 1 and will go back to 0, 0. Means this 4-bit counter counting numbers from 0 to 4 ones and after 4 ones, again go back to 4 zeros. Is it clear? Is it clear?
Yes, sir.
So this is how a binary ripple counter with we can have with T and D flip flops also, but T is the most popularly used ripple counter. So this is binary ripple counter. Remember, the name itself will let you know it is ripple because there is no common clock. The clocks are connected to different sources. The clock input of the first flip flop connected to counters. The clock input of the second flip flop connected to the previous flip flop output. This clock is connected to A1. This flip flop clock is connected to A2. See, since the clocks are connected to different sources, we call it as a ripple counter. Why it is called binary? Because it counts from 0, 0, 0, 0 to 1, 1, 1, 1, and after 4 ones it again go back to 0, 0, 0. Means it counts binary numbers. Hence we call it as binary ripple. Clear? Yeah. And moreover, we can say this is also called as binary up counter. Means it is counting from 0 to 15. That is called 4 zeros to see this counter, this specific circuit diagram counts numbers from 4 zeros to 4 ones. 1, 1, 1. Right? And we can design binary down counter also. Means a counter which counts numbers in reverse sequence. See, if your counter counts from 15 to 0, that is 4 ones, 1, 1, 1, 1, 2, 0, 0, 0, 0, then we call it as a down counter. How do we do that? Very simple. A binary down counter can be constructed by simply removing this bubble. Remove this bubble. Remove this bubble. Remove this bubble. Remove this bubble. That's all. This is a down counter. See, if there is no bubble here, then every clock pass, every flip flop will be complemented. And previous flip flop is 1. In the earlier example, if the A0 is 0, A1 gets complemented. If A1 is 0, A2 gets complemented. If A2 is 0, A3 gets complemented. Now other way around, down counter. I'll show you the design of binary down counter. What do you mean by binary down counter? A binary count down counter. A binary counter with a reverse count is called as a binary countdown counter. It's a counter which counts in reverse order, like 15, 14, 13, 12, 11, and so on and so forth. In a downward counter is decremented by 1 with every count pass. Okay. How do we design this? If negative edge triggered flip flops are used, see, therefore, the diagram of a binary countdown counter looks like a binary ripple counter provided all flip flops trigger on the positive edge. See, instead of this negative edge that is called bubble, if you can remove this negative edge, we call it as a positive edge triggered flip flops. Means the flip flop will be triggered when the value of the clock becomes 1. See, in the earlier example I told, when count is 0, in the earlier example, I showed you, if count is 0, clock becomes active. If A0 is 0, since 0, there is a bubble, 0 becomes 1, clock becomes active. So this clock will be active if the input is 0. That is called negative edge. If you remove these bubbles, then it becomes a down counter. But the logic is very simple. A down counter can be easily constructed by removing the bubble before the clock pulses. This is how binary countdown counters are constructed. Now the next one is called BCD ripple counter. So in the earlier one, we have designed a binary counter, means the counters counts binary numbers. Now we are going to see BCD counter. What do you mean by BCD counter? We know what is a BCD number. BCD number starts from 0000. That is called number 0. BCD number starts from 0. From 0 it goes to 1. From 1 goes to 2. From 2 goes to 3. 3 goes to 4. 4 to 5. 5 to 6. 6 to 7. 7 to 8. 8 to 9. Back to 0. Because we know BCD numbers are in the range of 0 to 9 only. 0 means 0, 0, 0, 0. 9 means 1, 0, 0, 1. BCD counter counts only from 0 to 9. That is called 4 zeros to 1001. Now we will see how do we do this. How do we do this? So we have, since it is a ripple counter, there is no common clock. We have to observe the patterns. We have to observe when does the flip flops get complemented. See, so 1, 2, 3, 4 flip flops I am using. Yes or no? Because in a state diagram, every bit represents a flip flop. See, the first flip flop 0 becomes 1. The next state again 1 becomes 0. 0 becomes 1. 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 Means out of these 4 flip flops, let me call these flip flops as Q8, Q4. I have been using these names for flip flops. Q8, Q4, Q2, Q1. So there are 4 flip flops. The first flip flop, that is called Q1. If you carefully observe, it keeps changing. 0 becomes 1, 1 becomes 0. 0 becomes 1, 1 becomes 0. The first flip flop will be complemented always. Is it clear? So this is how we have to understand the transition sequences of flip flops. So what did you understand? The first flip flop Q1 changes after every clock pulse. That is means the first flip flop. Now we have to understand Q2, the second flip flop. In the logic, Q2 complements every time Q1 goes from 1 to 0. Q2. Now my logic, my intention is to understand Q2. See, this is my Q2 flip flop, means second flip flop. This is the second flip flop. Second flip flop means Q2 means second digit. Understand? Q2 means the second digit. Okay, what can we do? You see how it is changing. So Q2 is first 0 and in the second state also 0. But here it became 1 and again 1. Again 0. Again 0. Again 1. Again 1. Again 0. Again 0. Again 0, 0. Means for 2 times it is 0, for 2 times it is 1. So how do we understand this? See the logic. Q2, I am writing a logic for second flip flop that is called Q2. Q2 complements every time when Q1 goes from 1 to 0 as long as Q8 0. When Q8 becomes 1, Q2 remains at 0. Let us first think of this point. What did I write here? Q2 remains at 0 when Q8 is 1. See, when Q8 is 1, see Q8 is here 1 and Q8 is here 1. So that's why my Q2 is 0. Means my Q2 remains 0 when Q8 becomes 1. Okay, so Q2 is understood. See, when Q8 becomes 1, Q2 remains at 0. Okay, the logic is understood. What is another point? See, Q2 complements every time when Q1 goes from 1 to 0. Let us understand this. See, when Q1 going from 0 to 0 to 1. So Q2 remains at 0. Q2 is not changing. See, when Q2 goes from 1 to 0, Q2 complements. So there are 0, 1, 9. See, again Q1 goes from 0 to 1. So Q2 remains 1 only. See, when Q1 goes from 1 to 0, Q2 complements. Yes. See, when Q1 going from 1 to 0, the Q2 complements 1 becomes 0. Again, you see 0, 1, no change because 0, 0. See, when Q1 goes from 0 to 1, it will be no change. But you see here, when Q1 goes from 1 to 0, Q2 complements. Yes, complemented. 0 becomes 1. See, again, it's going from 0 to 1. So, Q2 remains 1 only. When it come to here, there is a different rule. When Q8 is 1, Q2 remains at 0. This is how we understand the second flip-flop transitions. So what do you understand from this first these transitions of the diagram? First point, Q1 changes after every clock pulse. So there is no rule for Q1. Means first flip flop, every time it will change its value. But when you come to second flip flop, we have two rules. First rule is Q2 complement when Q1 goes from 1 to 0. Q8 becomes 1, Q2 remains at 0. So say two rules are over. Now let us look at the third flip flop, how it is being changing. So this is my third flip flop. 1. This is my third flip flop. 0, 0, 0, 1, 1, 1, 1. It is 0. How do you understand this third flip flop? Very simple. See, third flip flop means nothing but Q4. Okay. Q4 complements every time when Q2 goes from 1 to 0. Only single rule. See, Q1 have only one rule. Q2 have two rules. Q4 is also having only one rule. What is the rule for Q4? Q4 complements every time when Q2 goes from 1 to 0. Let us see whether it is happening or not. See, when Q2 goes from 1 to 0, see Q2 going from 0 to 0. So my Q4 is same. Q2 grow from 0 to 1. So my Q4 is same. Q2 go from 1 to 1. So my Q4 is same. 0 to 0. When Q2 go from 1 to 0, yes, here it happened. Q2 going from 1 to 0. Hence, my Q4 gets complemented. 0 becomes 1. Okay. Again, you see, Q2 go from 0 to 0. Hence, my Q4 is same. Q2 go from 0 to 1. Hence, my Q4 is same. When Q2 go from 1 to 1, my Q4 is same. When Q2 go from 1 to 0, yes, here I got it. See, when Q2 goes from 1 to 0, my Q4 complements. See, 1 becomes 0. When Q2 go from 0 to 0, no change, so 0 becomes 0. So is the rule satisfied? Can someone respond to this? Hello? Can someone respond?
Yes, sir.
So now we will look into Q8. What happens to Q8? Q8 remains at 0 as long as Q2 or Q4 is 0. Now let us look at see. Q8 remains at 0. See, Q8 is 0 here, 0 is 0, 0 here, 0 here, 0 here, 0 here, 0 here. The Q2 remains at 0. Why? Either Q2 or Q4. There must be 0 in either Q2 or Q4. See here Q2, Q4 both 0, hence Q8 is 0. Q2, Q4 both 0, hence Q8 is 0. Here Q2 is 1, Q4 is 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1. So we have to so for all these states, the first rule holds. What is the first rule for Q8? Q8 remains at 0 as long as Q2 or Q4 is 0. Next, when Q2, Q4 both becomes 1, means this one in all states. These 4 states come into this one. When Q2, Q4 both becomes 1, see, Q8 complements when Q1 goes from 1 to 0. Okay, means when both Q2, Q4 becomes 1, Q2, Q4 both becomes 1, Q8 complements when Q1 goes from 1 to 0. But it is 0 to 1, hence Q8 is no change. When Q2, Q4 both ones, when Q1 goes from 1 to 0, Q8 complements, see, 0 becomes 1. So these are the rules for Q8. These are the rules for Q8. So now let us slowly look at, read out all these rules, and we will see how do we incorporate these rules into drawing the diagram. So Q1 always changes. So let me draw the diagram. See, this is my Q1 flip-flop. All flip-flop, this Q1 is a flip-flop of what type? JK. Both J and K are connected to logic 1. Means when J is 1, K is 1. Means this flip-flop is ready to be complemented. Because when we know when a GK flip-flop, J is 1, K is 1, clock is active, this flip-flop will be complemented. See, as and when you press count, since J is 1, K is 1, Q1 keeps complementing. That's what we wrote. Q1 changes state after every clock pulse. So as and when this clock is active, since J, K are 1 and 1, this Q1 will be complemented every time. Now let us go to Q2. Otherwise, we let us see Q4. Very easy. Q4 complements every time when Q2 goes from 1 to 0. Let us go to Q4. See, this is my Q4. Q4 complements every time because see, what is this J? See, this K is always 1. See, K is connected to 1. So to complement Q4, we need K to J to be 1 and K to be 1. See, J is connected to Q1. So when J becomes 1, when Q1 becomes 1. That's what I wrote here. When Q2 goes from 1 to 0, Q4 complements. The clock is connected to Q2. So if this clock need to be active, means Q2 need to be 0 because there is a bubble before negative edge taken flip-flop. Means this flip-flop will be complemented. See, this is not the line. This is the wrong line. Both J is 1 and K is 1. Both are ones. Means J is 1, K is 1. Means this flip-flop Q4 is ready to be complemented, waiting for clock. So clock becomes active when Q2 is 0. That's what I wrote. When Q2 goes from 1 to 0, Q4 complements. Over. Now let us see. Now let us see Q2. How you can understand Q2? Is Q2? Q2 complements every time. Q1 goes from 1 to 0 as long as Q8 is 0. Remember this? Q2 complements every time when Q1 goes from 1 to 0 as long as Q8 is 0. See Q2. So if you want to Q2 to be complemented, the J to be 1, K to be 1. See, K is already 1 because K is connected to 1. When J becomes 1, J becomes 1 because J is connected to Q8 bar. Means when Q8 is 0, J becomes 1. That's what I told you. Q8, as long as Q8 is 0, means Q8 must be 0 to Q2 to be complemented. So when Q8 is 0, this J becomes 1. K is already 1. The clock is connected to Q1. See, that's where I wrote Q2 complements when Q8 is 0 and Q1 goes from 1 to 0. So when Q1 goes from 1 to 0, means when Q1 is 0, this clock is active. When Q8 is 0, this J is 1, K is already 1, so Q2 is ready to be complemented. That's what I wrote. And go to Q8. Q8 remains at 0 as long as Q2, Q4 is 0. Okay? I'm using J, K is connected to 1. J is connected to an AND gate. AND gate is receiving Q4. See, either K for Q4 is 0 or Q2 is 0. If any one of them are zeros, this AND gate is 0. Means J is 0. In JK flip-flop, when J is 0, K is 1, next state is same. No change. Now you see, when both becomes 1, when Q2, Q4 both becomes 1, Q8 complements when Q1 goes from 1 to 0. That's what I wrote. So the second rule for Q8, when Q2, Q4 both becomes 1, means Q2 1, Q4 1. So this is 1, this is 1. So this J is 1. K is already 1. So Q4 is ready to be complemented. Waiting for the clock is coming all the way from Q1. Means when Q1 is 0. That's what I wrote. When Q1 goes from 1 to 0, means when Q1 is 0, when Q2, Q4 both becomes 1, the flip-flop Q8 will be complemented. This is how we have incorporated all said and done rules into the design aspect. This is a problem with ripple counter. We have to understand how does flip-flops changing their state. Otherwise, we cannot do it. That's all for today. Thank you very much.